Excuse me, you're muted.
All right, sorry. So I think I was muted on Zoom. So what we are talking about is the transistor can be in different regions. Of course, it can be in cutoff, it can be in triode, it can be in saturation, and so on. And we know that the transistor, if you plot the VTC, initially the transistor is in cutoff. So of course, your input voltage is small, and if it does not reach your threshold voltage, then the transistor is in cutoff, and the output is close to VDD. Right after your input reaches VT, your VGS minus VT is just a little bit higher than zero, right? Because VGS is your input. Just when your input crosses VT, you are a little bit higher than zero, and your output, which is VDS, is much, much higher than zero. So, of course, the transistor turns on in saturation. So, this is the region when you have saturation, and you already know that this is the region where you have gain in the from the voltage transfer characteristic. And then at some point, when VDS becomes lower than VGS minus VT, which will happen over here at large VGSs, then the transistor goes into triode. So this is the triode region, this is the saturation region, and this is where you have the transistor in cutoff. So of course, for gain, you want the transistor to be in saturation region. And for that, whenever we are trying to do any kind of analysis with transistor-based amplifiers, we'll try to make sure that the transistor is in saturation, and that will be called the DC analysis. Of course, you might have heard about DC analysis and AC analysis. DC analysis makes sure that the transistor is in saturation and your biasing is correct. For that, you just find the operating point. One way that we'll be seeing in the example problems is that you can start with assuming that you're in the active region. So you'll be using the active region formulas or the saturation region formulas, which is ID, or the drain current, is equal to K over 2 times V overdrive squared, which means V overdrive is going to be square root of twice ID over K, where K is mu times COX times W over L, or K prime times W over L. And in most problems, you can assume 1 plus lambda VDS to be almost equal to 1, or lambda to be almost equal to 0, unless I state otherwise. Unless I give it in the problem that your lambda is not 0, you do not need to consider lambda. So you can consider your lambda channeling modulation parameter to be equal to 0, which means that the output resistance is going to be infinitely large in that case. Because the output resistance of the MOSFET, which is RO, something that we proved in the last class, is equal to 1 over lambda ID. All right. And then you'll solve all the equations and then verify that your VGS is greater than VT and VDS is greater than V overdrive. And indeed, if these two equations hold true, then you are in the active region. And if you are in the active region, you can expect gain out of the transistor. So that's all about DC analysis. Now, the next part, which would be basically your homework number 5, is the AC analysis of the transistor. Right? How much gain does the transistor provide? We know that the transistor is in saturation and it can provide gain. But how much? What is the amount of gain that we want to have or we can have from the transistor? That's what we'll understand from the AC analysis, which is also called the small signal analysis, because your AC input is a small signal. If your input is large, you do not need gain. Only because your input is small, you need gain, right? Or you want gain. Now, that is why AC analysis will also be called the small signal analysis, and the transistor has a small signal model, which we discussed in the last lecture. And we'll be using that small signal model to calculate the AC gain. Two very important considerations, or two very important variables that we'll be using during our AC analysis is called GM, which is the transconductance of the MOSFET, which is nothing but the derivative of your ID current with respect to VGS. VGS is your input and ID is your output current, right? So your input is a voltage quantity, output is a current quantity. So basically your transfer function is a conductance. So if the transfer function is a conductance, that's why we are calling it a transconductance parameter. So if you take a derivative of ID with respect to VGS, you'll get your GM, or the transconductance. And you'll see that that will be equal to K times VOV, because if you just take a derivative of this, and let's say you just neglect 1 plus lambda VDS for now. So in that case, you'll have, if you just take a derivative of ID with respect to VGS, you'll get K times VOV. You can also represent that as twice ID over VOV, or square root of twice K times ID. This is basically the same equation as we had proved in the previous classes. The other parameter is GO, or basically the output conductance. So G represents the conductance, and GO is for the output conductance, and conductance is nothing but 1 over resistance, right? So from Ohm's law, you know about resistance, conductance is just 1 over resistance. So basically this output conductance is the derivative of this ID equation with respect to VDS, because ID is your output current, VDS is your output voltage. The small change in your output current as a function of a small change in output voltage, that is going to be your output resistance, right? Or output conductance in this case. So del ID over del VDS is your output conductance, and del VDS over del ID is your output resistance, just from Ohm's law, right? And we have also proved this, that if you take a derivative of ID with respect to VDS, you'll get lambda ID, or almost equal to lambda ID, which means RO, which is 1 upon GO, is going to be 1 over lambda ID. Where are we going to use these equations? We already saw that the basic equation for gain is over here. So these are the small signal models, or the AC analysis models of the transistor. In the left hand side scenario, you just have GM times VGS. So if you have an input voltage of VGS, or a small change in your input voltage, that's what you're representing with this lowercase VGS over here. Now GM times VGS will give you a small change in the output current, right? Because GM is the transconductance, multiply that with voltage, you'll get the output current. Also, the right hand side model is basically a little bit more complex than the left hand side one, where you are also taking into account the effect of RO. So RO is equal to 1 over lambda ID. RO is equal to 1 over lambda ID. And if your lambda is equal to 0, of course, RO is infinite, and that's what you have in the left side diagram. So in this case, on the left side, your RO is infinitely large, and that's why you don't show it in the diagram, because that's an open circuit. Infinite resistance is nothing but an open circuit. Now, we also proved in the last lecture is that your gain is going to be, or voltage gain in this case, is going to be the output voltage divided by the input voltage. And that is going to be of the form of minus GM times RD. Or if you take this RO into consideration as well, then it's RD in parallel with RO. Right? Because again, let's go back to the actual circuit diagram where we started with. So if this is your MOSFET, and if you have connected a resistance at the drain, your source is grounded, that is the common terminal, and that's why this configuration is going to be called a common source configuration, or CS, because your source is the common terminal between your input and output. Your input is provided between gate and source. Your output is observed between drain and source, right? And we proved this, again, this is just a recap of what we learned in the last lecture, is your voltage gain, which is equal to output voltage, that's VDS, divided by input voltage, that's VGS. Output voltage is going to be output current multiplied with output resistance. And output resistance, in this case, if you're looking at the resistance at the output terminal, you'll see a resistance looking up, which is equal to RD. You'll see a resistance looking down, which is basically the drain resistance of the transistor. That's something we already saw is going to be equal to RO. So the resistance that you see looking into the output terminal is this resistance looking up, that is RD, and another resistance looking down, that is equal to RO. Now, remember that this is a common terminal, the drain terminal is common. The top terminal of the RD resistance is connected to VDD, which is an AC ground. The bottom terminal of this MOSFET, the source terminal of the MOSFET, is connected to ground, which is also an AC ground. So if you are doing an AC analysis where you are only interested in AC parameters, not in the DC parameters, you're assuming that the DC biases have already been set and the transistor is in saturation already, right? And that's why you can isolate the DC analysis and AC analysis, and you can also think of it as an application of your superposition principle. What does superposition principle say? That if there are two voltage sources, of course, I'm simplifying it, but if there are two voltage sources, you can consider the effect of each of the voltage sources separately and add all those effects up eventually, right? So if you have a AC component and a DC component, you can say my DC component is a voltage source, my AC component is another voltage source. So in my DC analysis, I'll only consider the DC and analyze and figure out whether the transistor is in saturation. And during AC analysis, I'll assume that my DC analysis has been done, and I'll only analyze for the gain. So it's The DC and AC analysis is just an application of the superposition principle with which you can isolate the DC and the AC. So if that is true, which is, of course, it is true, then in that case, you have to, you can consider the VDD as well as the ground, both of them as AC ground. So in terms of AC, your VDD and ground, these 2 points are the same points because there is no AC fluctuation on your VDD, there is no AC fluctuation on your ground. So both of them have AC equal to 0. And in that case, you see that the resistance looking up and the resistance looking down are in parallel with each other because this point is common and the topmost and the bottommost points are also the same with respect to AC. With respect to DC, they are different, of course. But with respect to AC, they are the same point. And that's why the resistance looking into the drain node is going to be a parallel combination of your RO and your RD. Now, if your RO is infinitely large, that is the 1 upon lambda ID of the transistor. If lambda is 0, RO is infinitely large. So RO parallel with RD is just going to be RD. So that's the output resistance in this case. So output current multiplied with output resistance gives you output voltage, that's VDS. And your input voltage was VGS anyway. Now ID divided by VGS in terms of small signals or in terms of these lowercase parameters is your GM. That's the AC transconductance parameter. So you can write your AV voltage gain as minus GM times RD. Okay. And if you do not want to neglect RO, if lambda is not 0 and RO is not infinite, then of course you'll have minus GM times RD in parallel with RO, which is what we have written in the next page, that your voltage gain is equal to minus GM times RD in parallel with RO. Okay. So if you want to find out the voltage gain, all you need is to find out GM and all you need to find out RO, which is 1 upon GO. So if you just find out GM and GO, you are done. You have done the AC analysis, you know what is the gain of that MOSFET based configuration, right? So that's what we're going to do in AC analysis. That will represent the gain in the form of this GM times RD or minus GM times RD, whatever form it is. And then you're just going to find out what is the GM and what is the resistance at the output. The multiplication of GM and the output resistance will give you the voltage gain all the time. Okay. All right. So with that, let's quickly take a look at the similar problems of homework 4, which is nothing but your DC analysis of the MOSFET. And I know Shah has gone through some of these problems in the class last Wednesday's lecture, but I just wanted to go through them once myself. And if you have any questions, please feel free to ask. So of course, these problems are very similar to your actual homework 4 problems. In this case, for the first problem, your VDD is plus 7 volt, VSS is minus 7 volt. There is a RS resistance connected at source. There is a RD resistance connected at the source. And you're asked to find out the values for RS and RD so that the current is 2 milliampere. The current flowing through this is going to be 2 milliampere. Again, remember, there is no current flowing into the gate or out of the gate because the gate is an insulator. So the current at the drain will be same as the current at the source, and that current needs to be 2 milliampere. Now, assuming current ID equal to 2 milliampere, what is the largest value of RD for which the FET stays in the saturation region or the active region? That's what is also asked in the question. So to find out, let's say RD, which is a very easy problem to solve, finding out this resistance, that's very, very easy. Why? Because you know VDD, which is plus 7 volt. Okay. You have an idea about the VD node or the drain node over here, and then you have an idea about what is going to be the current, right? So the drain node is given to be 2 volts. This is at 2 volts. This is at 7 volt. So you have 7 minus 2 divided by 2 milliamperes. That's going to be the resistance value of your RD. Now, I guess there is a small typo over here. So this needs to be 2, but this is basically 7 minus 2 divided by 2. So RD is going to be 2.5 kilo. So that's why I said that it's a very, very easy problem to solve. That's what is going to be your RD if this point is given to be 7 and drain voltage is given to be 2 volts. Right? It's just Ohm's law. Now your VD is at 2 volts. This point is at 2 volts. Your gate is at 0 volts because that is connected to, let's say, ground directly. So VGD, which is the gate to drain voltage, is minus 2 volts. And there are multiple ways to find out whether the transistor is in active region. So what we wanted to remember was basically if your VDS is higher than V overdrive, then the transistor is in active region, which is same as saying your VD minus VS is higher than VGS minus VT. Now VGS you can write as VG minus VS. So VD minus VS is going to be larger than VG minus VS minus VT. Now you have VS in both left and right hand side, so you can just cancel out VS. So what you have is VD greater than VG minus VT. Or you can write that as VT greater than VG minus VD. So this is just mathematical manipulations. And then you see VT higher than VGD. That would be the condition for your active region. So this is what you have over here. Your VGD is lower than VT, or VT is higher than your VGD. Because your VGD is minus 2 volt, which means that the transistor is in the active region. And if the transistor, yes, question. So your VD is given to be 2 volts. And this is connected to ground, so this is 0 volts. So 0 volt minus 2 volt will give you the minus 2. Right? So VD is 2 volts, VG is 0 volts. So VGD is VG minus VD, which is 0 minus 2 volts. That is minus 2 volts. And in that case, you know that the transistor is in active region if your VGD is lower than your VT. So if you apply the active region or the saturation region formula now, so ID is equal to K over 2 times VGS minus VT whole squared, or V overdrive, which is just VGS minus VT, that is equal to square root of twice ID divided by K. Now here you know ID, you also know K because K is given in the question, 25 milliampere per volt square. So V overdrive is 2 times 2 milliampere divided by 25 milliampere per volt square, and that gives you 0.4 volts as your V overdrive. So now you know your V overdrive, which is VGS minus VT. So VGS is VT plus V overdrive. And VT is given to be 1.1 volt, that's your threshold voltage. So 1.1 volt plus 0.4 volt, that is 1.5 volt, that's your VGS. Of course, your VGS is higher than your VT. That is the reason why the transistor is on, and you have already found out the transistor is on in the active or in the saturation region. All right. So now that you know your VGS, which is 1.5 volt, you also already know your VG. You know your VG, which is 0 volt. What you did not know is what is your VS, right? And because you did not know your VS, you could not find out what is the value of RS. But now that you know your VGS from this transistor equation, from this equation basically, now that you know your VGS, which is 1.5 volt, you can write your VS, which is VG minus VGS, that is equal to minus 1.5 volt. So 0 volt is your VG. This is your VG, which is 0 volt. The voltage drop from gate to source is something that you found out to be 1.5 volt. So that means that the source is at minus 1.5 volts. And if the source is at minus 1.5 volt, you can find out what is going to be your RS, because again, you know your VS, that is minus 1.5 volt. You know the lower terminal of the resistor, which is at minus 7 volts. So the voltage drop across the resistor is minus 1.5 minus of minus 7. So 5.5 volt is the voltage drop across that resistance. And you already know the current, which is basically same in the drain as well as in the source, and that current is equal to 2 milliamp. So if you know the current and if you know the voltage drop across the resistor, you can find out what is the value of that resistor. Okay. So these value of the resistor, so RD equal to 2.5 kilo ohm and RS equal to 2.75 kilo ohm, that ensures that now you have a current of 2 milliampere through this drain to source. And at the same time, you also found out that the transistor is in saturation region or in the active region. Now, the second part of the question is pretty interesting, that assuming your ID is still 2 milliampere, what is the largest value of RD for which the FET will stay in the active region? Because your RD, so in this case, you try to find out what is the value of RD if you assume that your VD is equal to 2 volts. But if you let your RD change and want to keep your current constant, then of course this VD will also change. The drain voltage of the transistor will change, right? Because the current is same, the resistance is changing. So of course the voltage drop across the resistance will change. That means that the drain voltage of the transistor will change. Now, as the drain voltage of the transistor is changing, at some point VDS will not remain higher than V over drive. Right now, like with the values that you calculated, the VDS is higher than the V over drive. But if you keep on increasing the value of this resistance, keeping the ID current constant, the voltage drop across the resistance will keep on increasing. And at some point, the VD will be so low that the transistor will go into the triode region, because VDS will start becoming lower and lower as VD is going lower. And why is VD going lower? Because you're increasing the value of RD, because you want to find out the largest value of RD for which the FET stays in the saturation region. All right. Now, to find that out, what we did is that we wanted to find out what is the VD min for the active region. Now, what is VD, the minimum VD for active region? You can write that down as, so let's again go back to this curve that we always draw. Your VDS is on the x-axis and your ID is on the y-axis. When we derive the equations for the different regions in the class, so basically this is the region when you have triode, and this is the region when you have saturation. What is the boundary between those two regions? It's VDS equal to V over drive. Right? If VDS is lower than V over drive, you are in the triode region. If VDS is higher than the V over drive, you are in the saturation region. So V over drive is also called the VD for which you just start the saturation region. So that is also called VD sat. So VD sat is nothing but your V over drive, because that is the boundary between your triode region and the saturation region. Or it is also, you can say that it is the minimum VDS that you need to be in the saturation region. The minimum VDS that you need to be in the saturation region, that is defined as VD sat in like MOSFET terminologies. And the value of VD sat is equal to V over drive. All right. So you know VS. Now, that basically says that what is the minimum VDS for active region? The minimum VDS for being in the active region is V over drive, right? So you can call that VDS min. So VDS min is equal to your V over drive, right? So what we are interested in finding out that what is the VD min? Because VDS is VD minus VS. So VD min is going to be V over drive plus VS. And that's just because VDS equal to VD minus VS. So VD min is equal to V over drive plus VS. You already know the value of V over drive, which is 0.4 volts. You calculated that somewhere over here in the first part of the question. And you already found out what is the value of VS, which is equal to minus 1.5 volt. That's also you found out in the first part of the question. So you know your VS, you know your V over drive, you just add both of them up. So minus 1.1 volt is your minimum value of VD for which the transistor will be in saturation. If VD reduces any further, you'll go towards this left side region where the transistor will be in triode. So your VD min is minus 1.1 volt. And if your VD min is minus 1.1, so what we are saying is that instead of this 2 volt, if VD is reducing to minus 1.1 volt, even then the transistor will be in saturation. But if VD reduces any further, then the transistor will go into triode. Right? Because Vs has to be minus 1.5 volt because your ID is 2 milliamperes and RS is, let's say, this 2.75 kilo ohm. So the voltage drop across RS is going to be fixed. That means the value of Vs is going to be fixed at minus 1.5 volt. Now here in this case, your VD was 2 volt, Vs was minus 1.5 volt. So your VDS was 3.5 volt, which is larger than V over drive. That's why you were in the saturation region. But as you keep on reducing your VD more and more, at some point it will be equal to your VDS will be equal to V over drive. And after that, the transistor will go in the triode region. So VD min can only be minus 1.1 volt because V over drive is equal to 0.4 volts. Right? So VD min is going to be, or VDS min is going to be equal to V over drive, which is 0.4 volt. And that means VD min can only be minus 1.1 volt because Vs is already fixed at minus 1.5 volts. So if your VD min is minus 1.1 and your VDD is 0.7, you can find out what is the maximum value of RD, what is the largest value of RD for which the transistor will still be in the saturation region. Okay. And that's what we have here, that your RD max is 7 volts minus of that minus 1.1 volt divided by 2 milliampere, that's the current, that is 4.05 kilo ohms. So you can keep on increasing the value of your RD till 4.05 kilo ohm, but after that the transistor can go in triode region. All right, so that's your question number 1. Question number 2 is, again, a very similar problem, that here the FET has a VT of 1.1 volt, K equal to 25 milliampere per volt square, lambda is equal to 0. You want to find out the value of R needed to get ID to be equal to 0.5 milliampere. You want to find out the value of this R, the resistance RS, for which the current is equal to 0.5 milliampere. And the second part of the question is, if that resistance is equal to 5 kilo ohms, you want to find out ID and Vs. Okay, so to solve the first part, again, you can see that your VGD, your gate to drain voltage, is equal to 0 because gate and drain are connected together. If gate and drain are connected together, then VGD is equal to 0, and that is lower than the threshold voltage, which is VT equal to 1.1 volt. So if VGD is lower than VT, we know that is another form where you can represent, maybe I can also show that equation where we, so what here, that when we are discussing about these MOSFETs for the first time, we discuss all these equations, right? That when you are in the active region or in the saturation region, you basically say your VDS is greater than V over drive, but that can also be represented as VGD less than equal to VT. So both of them mean the same thing because these are just mathematical manipulations. So by using that same formula, VGD is lower than VT, you know that the transistor is in the active region. And because of that, you can use the active region formula. What is the active region formula? That ID is equal to K over 2 times V over drive squared. Or V over drive is square root of twice ID over K. Now ID is given 0.5 milliampere. K is given 25 milliampere per volt square. So you can find out what is your VOV. That's going to be 0.2 volts. VT is given. VOV is VGS minus VT. So if you know VOV and you know VT, you can find out VGS, which is nothing but V over drive plus VT. V over drive is 0.2 volts and VT is 1.1 volt. So VGS becomes 1.3 volts. Now, if your VGS is 1.3 volt, that means the drop from gate to source is 1.3 volt. What is the gate voltage? Because the gate is connected to drain, the gate voltage is equal to 6 volt. And this is 6 volts. And so that means that the gate voltage is also 6 volts. So what would be the source voltage? The source voltage would be 1.3 volt lower than 6 volts because VGS is going to be 1.3 volt. So VS is going to be 4.7 volts or something like that, right? 6 volt minus 1.3 volt, that would be 4.7 divided by 0.4, 0.5 milliampere, that's the current. That will give you the value of this resistance RS, that is 9.4 kilo ohms. Now, the second part of the question is that if this resistance is 5 kilo, you want to find out ID and Vs. The first part was easy. That analysis was easy because you had all these terms known, that your V overdrive was something you could find out because ID was fixed. Your threshold voltage was fixed, so you could find out VGS as well. But for the second part of the question, you're just given the value of RS and you're not given the value of ID. Okay? Because you're not given the value of ID, you cannot find out the V overdrive. If you cannot find out V overdrive, you cannot find out what is VGS. If you cannot find out what is VGS, you cannot find out what is going to be the source voltage. So for the second part, only because the R is given, but ID and Vs both are now unknown. In the previous case, ID was known, and that actually fixed the VGS value or the V overdrive value. In this case, both are unknown. So you kind of, if you're trying to use this particular equation, then you're kind of in a loop that you cannot actually find out what is your ID and what is your Vs. So your VOV is also unknown. So everything seems to be an unknown here. But the way that you can still solve it is called an iterative process, that you can assume a solution. Let's say you can guess a particular ID. Let's say I guess ID to be equal to 1.1 milliampere initially. So if my ID is 1.1 milliampere, my VOV is going to be, you can calculate what your VOV is going to be using the same formula over here. You can find out your V overdrive. If you find your V overdrive, you can find out your VGS. That is going to be 1.4 volts. So if you have find out your VGS, you can find out what is going to be your VS voltage. And from there, you can recalculate your ID. In that case, if your VGS is 1.4 volt, ID is going to be 6 volt minus 1.4 volts divided by 5 kiloampere, because 5 kiloampere is the value of the RS that is given. And with that, you end up with ID to be equal to 0.9 milliampere. So originally you had assumed ID is 1.1 milliampere, applied all the formula, and then ended up with an ID which is 0.9 milliampere. So it did not match. Now you can assume that ID iteratively, you can keep on solving this. And that's how, let's say, most of the solvers, the CAD tool solvers do it using an iterative fashion. That if your ID is 1 milliampere instead of 1.1 milliampere, you can again calculate VOV, you can again calculate VGS and ID, and then you will see that it will be closer to 1 milliampere. Right? So using that iterative process, you can still find out what is your ID and what is going to be your V overdrive in this case. All right. The third problem was probably the easiest. And I think you have a very similar problem in your homework number 4 as well. So in this case, you have a VT to be 0.7 volt, K is given to be 64 milliampere per volt square, lambda is equal to 0. You want to choose the value of RG1 and RG2. These are these biasing resistances. Again, we are only talking about DC analysis here. There's no question related to gain in your homework number 4, but homework 5 has the same set of circuits, but then you are asked to find out gain, or very similar circuits, and you are asked to find out gain. All right, so you want to find out RG1 and RG2 so that VG is equal to 4 volts and RG1 in parallel with RG2 is equal to 40 kilo ohm. So of course, this is given to be 10 volts. Now that you want to have VG to be equal to 4 volts, you know that the 60% of the resistance will be in RG1 and 40% will be in RG2. So that 60% voltage drop happens across RG1, that is 6 volts, and 4 volt voltage drop happens across RG2, totaling to be a total of this 10 volts, right? So you already know that RG1 and RG2 will be at a ratio of 6:4. And RG1 parallel with RG2 needs to be about 40 kilo ohms. So you can write down the formula for that, which is RG1 times RG2 divided by RG1 plus RG2, that is equal to 40 kilo ohms. And from those two equations, you can solve for RG1 and RG2, and they are 100 kilo ohms and 67 kilo ohms. Any questions related to some of these? Yes.
Where's the 0.4 volts?
Where does the 0.4 volt come from? Oh, okay. So, PDD. All right, sorry. So this is not 0.4. So this is 0.4 multiplied with 10. That is basically 4 volts, right? So 0.4 VDD, that's what you want to have. And that is basically 4 volts, which is your VG. Yeah. All right. So with that, I think all the questions in homework number 4 are relating to your biasing, or basically finding out the DC operating points of the transistor. And your goal is to make sure that the transistor is in the saturation region. So with that idea in mind, we'll start looking into AC analysis of MOSFET. And for that, the general analysis strategy would be the following. That first, you will try to draw the equivalent model of the MOSFET. So this is something that you have already seen when we are discussing the op-amp related problems, your homework number 2, homework number 3, and so on. That the op-amp has an input impedance, then the op-amp converts, let's say, this input voltage Vi into an equivalent current of, let's say, Gm times Vi. So there were 2 different models that we discussed. One was the Thevenin equivalent model, one was the Norton equivalent model. So basically, in Thevenin equivalent model, you have a VCVS, and Norton equivalent model, you have an output current source. So you have a VCCS, a voltage controlled current source for the op-amp. So till now, right now we are not discussing about MOSFETs. Right? We are starting from the point where we left off when we were discussing op-amps, right? But as you see that the model looks very similar. The AC equivalent model looks very similar. The only difference is that you had a input resistance Ri, right? Because op-amps could be non-ideal, and that non-ideality was implemented in the form of an input resistance Ri. For the MOSFET, right now we said that because you'll see the gate of a MOSFET, there would be no current going in. And in that case, your input resistance for the MOSFET could be infinitely large. Right? But right now we are talking about the general amplifier analysis, where let's say you can have an input resistance as well, because in the op-amp we did. Now you have, let's say, a VCCS based model. That means Gm multiplied with that input voltage will give you the output current. And then you'll have a output resistance of that amplifier. So let's call that RO. And the voltage that gets developed across RO is going to be your output voltage VO. Okay. What is GM? GM is a small change in your output current as you're making a small change in your input voltage. So basically derivative of your output current with respect to the input voltage. Now, so this is the model that we had drawn on the top. And then if you connect a voltage source over here, Vs, and assume that there is always a Rs source resistance with the voltage. And then on the output side, if you're connecting a load resistance RL over here. So you have solved very similar problems in your homework number 2, right? Or even homework number 1. Right? It's the same problem. You just have a model of your amplifier, and then you have a source, non-ideal source, and then you have a non-ideal load. Now, if you assume that RL equivalent is the total resistance from the output node to the ground, the output node is over here. The total resistance from the output node to the ground, let's call that RL equivalent. So RL equivalent is nothing but RO in parallel with RL. So RO is the output resistance of the amplifier, and RL is the actual load resistance that you have connected. So what is inside this green box is the property of the amplifier. These are not real resistances that you have connected in the circuit, or not real current sources that you have connected in the circuit. So whatever is inside this green box is the property of the amplifier. On the other hand, what is outside the green box is basically what you have connected in the circuit. So RL equivalent, the equivalent load resistance connected at the output node, is going to be RO in parallel with RL. Why? Again, that is very clear from this diagram, that if this is your output node, you have one resistance going to ground over here, that is RL, and the other resistance is inside the op-amp or inside the amplifier, which is RO. Again, just think about what you learned during op-amps. We are talking about the same thing over here. So RL parallel with RO, that's your RL equivalent. Your AVT, the voltage gain in the form of VO divided by voltage developed at the input terminal of the MOSFET or input terminal of the op-amp. So VO divided by VIT. So VO is the voltage at this node. VIT is the voltage at the input terminals of the amplifier. That is going to be GM times RL equivalent, right? Why? Because what is VO? What is VO? VO is just output current multiplied with output resistance. What is output current? Output current is GM times VIT, right? This is GM times VIT. That VIT is the voltage at the input of the op-amp. And GM times that voltage gives you the current. That current flows through the output resistance over here. The output resistance of the amplifier was RO, and you had connected another RL in parallel to RO. So what is the total resistance at that output node? That is going to be RO in parallel with RL. So current multiplied with resistance gives you voltage, Ohm's law. So that is equal to your VO. This is equal to your VO. So what is going to be VO divided by VIT? That's GM multiplied with RO in parallel with RL, or that is equal to RL equivalent. So GM times R equivalent will be the voltage gain for any amplifier. Because GM will relate your input voltage to your output current. Multiply that with your output resistance, you'll get your output voltage, right? Output current multiplied with output resistance is output voltage. Output voltage divided by input voltage is your gain, voltage gain. And GM is the quantity that is relating your input voltage with your output current. So that's how it all fits in. That your GM that connects your input voltage to your output current multiplied with output resistance gives you output voltage, and output voltage divided by input voltage is your voltage gain. Right? So any voltage gain equation will be of the form GM times R equivalent. Now, as you see here, that something that is different from MOSFET based equation, that we are writing this uppercase G then subscript M instead of the lowercase gm. The lowercase gm was the AC small signal equivalent quantity for the transconductance of the MOSFET. Here, you are actually representing the effective GM of the circuit or the entire system. Remember that when we talked about op-amp, op-amps always have this infinite input impedance or zero output impedance. But the overall system may not have infinite input impedance or zero output impedance. Similarly, if your transistor has a transconductance of GM and an output impedance of RO, so you know that the transistor has an transconductance of GM and the output resistance of RO. That's the property of the MOSFET. But the whole system may have a different transconductance and may have a different output resistance. Just like your op-amp, even though ideal op-amp had infinite input impedance and zero output impedance, but in the system, you can have a non-infinite input impedance and a non-zero output impedance. You already saw that in multiple examples earlier. Similarly, when the MOSFET is used in a system, the GM of the system may be different from the GM of the MOSFET. And the RO of the system may be different from the RO of the MOSFET. Right? That's what you have to keep in mind. And if you solve the GM of the system and RO of the system, multiply those two, you get the voltage gain of the system. So that's why I wanted to show this generalized form first before showing any other circuit. So all you need to do to find out the AC gain in a system is find out the effective GM and effective RL and multiply that. Of course, you may have other voltage division in the system. For example, this RS and RIT, they will create a voltage division, something that you solved in your homework 1, right? That the voltage VIT is just going to be RIT times the VS voltage divided by RS plus RIT. So you'll have this voltage division formula for RS and RIT. Similarly, there could be other voltage divisions at other points in the system as well. So that may reduce your overall voltage gain. But in general, whenever you're talking about these MOSFET-based circuits, your GM times R will be the general form of the equation with which you will try to find out the voltage gain. Okay. All right. So let's take a look at our first example. And looking at this example, it should be clear why we want to find out the effective GM and effective R out. So let's say you have this circuit. You have a gate voltage VG. Let's say this is an AC voltage. And let's just assume that the transistor is already in saturation. You have done the DC analysis. You already know how to do it. You have solved homework 4. And you're assuming that the transistor is already in saturation. That's the point for what we assume when you're trying to do the AC analysis or the small signal analysis. Okay. So you have a AC voltage at the gate. You have a resistance RS1 connected at the source. Now, this is something different, right? We did not talk about this. And that is why the problem or the solution that what is going to be my effective GM and what is going to be my effective Rout will be different because I now have a resistance connected at the source. The source is not grounded. Earlier, when we were discussing MOSFET problems, we assumed that the source is grounded most of the time. So how do we analyze this? The way to analyze this is that first you draw the small signal model of the transistor. So I would encourage solving as well. So there are many problems given in this notes. So try to solve all the problems by drawing the small signal model of the transistor first. And what is the small signal model of the transistor? That's very easy. So this is the transistor, and this is the small signal model of the transistor. That you have a VGS, a gate to source voltage, and GM times VGS will be the current seen at the output node, which is the drain node of the MOSFET. That's it. You don't need to consider RO for now. Let's just ignore RO because I mean you can always consider RO, but that will just make the problem a little bit more complex. Because we are learning about MOSFET for the first time, let's just ignore RO. So you say your input is VGS and your output current is GM VGS. That's it. No need to consider anything else. Now with that, so basically you're considering RO to be equal to infinitely large. With that, now what you have is that you have a source resistance connected here. So let me draw that with a different color. So you have a source resistance connected here, RS1. That's this RS1. Okay. Now what do we know about the transistor is that the transistor sees this VGS, get to source voltage, and converts it to an output current of GM times VGS. Why is the problem different now is that you are connecting a AC voltage source at the gate, so that's your VG, but you have no idea what your source voltage is, right? If your source was grounded, the problem was very easy. The gate to source voltage would be gate voltage minus source voltage. Because the source is grounded, VGS is equal to VG. Now the problem is a little bit more trickier. It's not as simple as that. Because your VGS is VG minus VS, and you do not have any idea about your VS. But is that really so? Do you have no idea? Of course, you can calculate what is your VS, and that's what is being done over here. That your VS is your current multiplied with RS1. There is a current flowing through, so this is the current. That current multiplied with RS1, that will give you the voltage VS, just from Ohm's law. So VS is equal to ID times RS1, and ID is equal to GM times VGS. So GM times VGS times RS1 is your VS. So now you have found out the VS, even though initially you were not very sure because source was not grounded. But you can find out your VS to be equal to GM VGS times RS1. So you can write your VGS as VG minus VS. VG is VG, and VS is something that you just found out, GM times VGS times RS1. So VGS is VG minus VS. Now you have VGS on the left side as well as the right side of this equation. Let's take VGS only on one side. So VGS multiplied with 1 plus GMRS is equal to your VG. Or your VGS is equal to VG divided by 1 plus GMRS. Now this is a very interesting observation because now you have found out your VGS to be equal to VG divided by 1 plus GMRS. So your ID, which is the output current, is GM times VGS is equal to GM divided by 1 plus GMRS times VG. All we did is that replace VGS, your VGS is here, right? Replace your VGS and you get this formula. So because your source was not grounded, what you see in this case is that your ID, which is GM times VGS, is equal to this GM divided by 1 plus GMRS multiplied with VG. So now you see your effective GM. If you consider your input voltage as this one, your effective GM that you see for this circuit is GM divided by 1 plus GMRS, where GM is the transconductance of the MOSFET. And that's why I said that the effective GM of the circuit may not be same as the GM of the MOSFET. GM of the MOSFET was just GM. lowercase gm that you see in the numerator. That divided by 1 plus GMRS is the effective transconductance of the whole system. And GM divided by 1 plus GMRS, you'll see it will be lower than original GM. So GM has reduced, and that's why this resistance is called a degeneration resistance. It degenerates the gain, it degenerates the GM. Okay. So let's stop here. We'll continue from this point on Friday.